Hello everyone, and welcome to week 9 of your Business 255 course. This is Dr. Matt C. Howard. This should be the week after the test, so hopefully you're happy with your test grade. Hopefully you're excited to continue your statistical education. So let's move on to the next unit, or the next section of material after exam 2. So this week we're going to be learning how to make inferences with regression. So before the exam we learned how to do regression with a single predictor. This lecture we're going to move into doing regression with multiple predictors and how to make predictions with regression. How to make inferences while using regression. So how can we run a regression, get some results, and then actually make predictions with that result, or with those results. That's the general idea of what we're learning today. So last class we learned about regression. Regression is used to, hopefully you remember, it's used to determine the linear relationships between an outcome and a predictor or predictors. So in the prior lecture, we just learned with one predictor, so we would say the relationship between an outcome and a predictor. But this time we're learning how to do regression with multiple predictors. So now we're saying the linear relationship between an outcome and predictors. And as we said before, when analyzing only two variables or just one predictor, it's almost identical to correlation. Well, what about when we analyze more than two variables? What if we have more than one predictor? How can we conceptualize, how can we think about regression? So now we're moving beyond just one predictor, now we're looking at two or more predictors. So regression still tries to find the test statistics that best describe the relationship between a predictor and an outcome when you have multiple predictors. So it still tries to provide the results that best describe, well, how do all of these predictors relate to that outcome? How do all of these predictors explain that outcome? And regression still tries to find those numbers. It still does it by looking at the smallest sum of squares. It tries to get the smallest differences between your observed data and your estimated prediction line. It still tries to find these best values. And when there's more than one predictor, it does this for each predictor in the outcome. So before we were just talking about we have an intercept and a slope. We would have a beta naught and a beta 1. And if you remember from last time, our beta naught was the intercept. It's just our one way to think of it is our baseline value. And our beta 1 was the slope. And it was for every one increase in the predictor, how much does our outcome change? And this is what it visually looked like when we had one predictor. As you can see, we had our beta naught, which is above the outcome, and we have our beta 1, which is above the line, because it describes the relationship. It tells us the magnitude and the direction of the relationship between the predictor and the outcome. When we're doing regression with multiple predictors, though, it looks more like this. We still have our beta naught, we still have that beta 1 for predictor A, but now we have another beta for each predictor. So in this example, we have predictor A, B, and C. So now we have beta naught, beta 1 for predictor A, beta 2 for predictor B, and beta 3 for predictor C. So each of these betas will describe each of these betas will each describe a different relationship. So beta 1 describes the relationship between predictor A and the outcome. Beta 2 describes the relationship between predictor B and the outcome. And beta 3 describes the relationship between predictor C and the outcome. So you might be asking yourself, so what's the difference between regression with multiple predictors and just performing multiple regressions with a single predictor? So the first obvious answer is if you're doing multiple regressions, each with a single predictor, it'll just give you the beta naught and the beta 1 independently. So this one could give you a beta naught and a beta 1. This one could give you a beta naught and a beta 1. And this one could also give you a beta naught and a beta 1. And if you ran 3 different regressions independently, you would have a different beta naught and a beta 1 for each one. But if you run it all together, you get a beta naught, a beta 1, a beta 2, and a beta 3 all together. It describes your entire model all together. You don't have to run all these different analyses, piecemeal it all together, and hope for the best. It runs it all together and it gives you all the results at the same time. However, perhaps more importantly, when analyzed together, regression estimates each relationship while controlling for the others. And this is a huge concept you should know. This is an extremely important concept. When analyzed together, regression estimates each relationship while controlling for the others. So it gives you the effect of, let's say, predictor A while controlling for predictor B and C. It gives you the effect of predictor B on the outcome while controlling for A and C. And then it gives you the effect of predictor C while controlling for A and B. And of course, you're probably asking yourself, well, what does that mean to control for others? What are you saying there? And in general, what it means to control for others is you're accounting for the variance explained by the other variables. So when you're saying control for others, that means you're still getting an estimate of those relationships, but you're deciding, well, there's some variance that should go to predictor A and not predictor B. There's some variance that should go to predictor C, but not predictor A. And you're trying to partition that variance. You're trying to partition how well each variable explains when accounting for the other. And another way to visually think about this is, let's look at Venn diagrams. If you were to do a regression in each of these predictors independently, it might look like this. You might have predictor A in the outcome, and there's a good amount of overlap there. You might get a moderate relationship. Now we have predictor B in the outcome, and once again, you might have a moderate relationship. There's a good amount of overlap. And if you were to run your final separate regression, you might have predictor C in the outcome. There might be a good amount of overlap, and you might have a moderate relationship. However, when you run your regression with all the variables put together, and let's just start with just two predictors, predictor A and predictor B, it might look like this. So as you can see in this example, there's some overlap. That predictor A predicts the outcome, predictor B predicts the outcome, but there's some space you can see right there in the dead middle that A and B overlaps with the outcome. So if you were to run your regressions independently, there's no way you could tell whether any of this variance overlaps. There's no way you could tell whether, well, the predictive ability of A might overlap with the predictive ability of B. But when you run a regression, regression partitions that variance. Regression figures out, well, there is this area of overlap. Which part of that overlap should be part of predictor A, and which part of that overlap should you attribute to predictor B? So when you run separate regressions, it might seem like you're explaining all this variance in the outcome, but when you run them all together, there might be a chance you're actually just overlapping the same predictors on top of each other, and you might not actually be explaining as much variance as you think you are. So when you run a regression with everything together, you're trying to figure out, well, how well do all these things predict the outcome when accounting for each other, when controlling for each other? And this diagram does a good job of displaying that. Your regression will determine, well, predictor A overlaps with the outcome, predictor B overlaps with the outcome, but there might be some where all of them overlap together. And it tries to figure out how to split that variance, how to partition that variance, to say, well, this is variance that actually predictor A explains better than B. Or maybe that part of the overlap in the center, some of that might actually be variance predictor B explains better than predictor A. And regression will figure that out for you. It will provide the numbers when accounting for that overlap. And here's another example. So in this one, we have three predictors like we were talking about before. We have A, B, and C in the outcome. And once again, regression will determine, well, how much of this overlaps, how much of that overlap in the dead center should go to A, how much should go to B, and how much should go to C. And it will provide the results for you when accounting for all of that overlap, when partitioning all that overlap. And it will give you the most accurate numbers, the most accurate results when accounting for the other variables. So when performing a regression with multiple variables, the results determine the variance in the outcome that can be attributed to each predictor. And in other words, it tries to figure out which parts of the overlap should go to each predictor. So if you're confused by this, if this isn't making sense to you, please pause the video, send me an email, because we're going to keep it at that. We're going to keep it, honestly, this is a little bit surface area. If you're taking a little bit more of an advanced stats class, we would get into the actual numbers. We might get actually into the calculations of how it determines that overlap, how it determines how to attribute that variance. But for this class, we're going to keep it just at that. We're just going to say it accounts for that overlap. We're not going to figure out the calculations. We're certainly not going to go do them by hand. But instead, we just need to know that when you're doing a regression with multiple predictors, it accounts for that overlap. It determines how to partition that variance that might be shared among your predictors. Okay, so if you get that, let's continue. So the results of a regression analysis with three predictors can be represented by the following formula. So this is just an example. If we had three predictors, what would our regression equation look like? And it looks very similar to what we looked at before with one predictor. We still have y hat, which is the predicted value, And then we have x1, which is the first predictor, x2, which is the second predictor, and x3, which is the third predictor. So one thing you might be asking yourself is, well, what's beta naught, beta 1, beta 2, and beta 3? Hopefully you can answer that yourself. Hopefully, based on what we learned in our last lecture, you already can guess what those mean. Beta naught is the intercept. So just like before, beta naught is the intercept. You can think of beta naught as the baseline. So when everything else is 0, when x1, x2, and x3 are 0, beta naught is what y hat will be. Beta naught is what our predicted value will be. So beta naught is our intercept. So then beta 1 is the slope of the linear relationship between the outcome and the first predictor. Beta 2 is the slope of the linear relationship between the outcome and the second predictor. And beta 3 is the slope of the linear relationship between the outcome and the third predictor. So as we can see, we can get our regression equation, we can get our regression results, and we can estimate based on beta 1, beta 2, and beta 3 what the relationship is between each of those predictors and the outcome. So let's say if our beta naught, like we learned before, is let's say 0.3, we would generally know then, oh, we might have a moderate positive relationship between our first predictor and our outcome. Let's say beta 2 is negative 0.1, we would maybe say, oh, we have a weak negative relationship between our second predictor and the outcome. And then let's just say beta 3 is negative 0.9. We would say, oh, we have a very strong negative relationship between our third predictor and our outcome. For example, of course they would differ whenever you run a regression, depending, and if you're looking at unstandardized betas, it would depend on the context. But based on our regression results, based on our regression equation, we can get a general feel or not even a general feel, we can identify the relationship between each of our predictors and the outcome. Also, before we looked at scatter plots and we drew the line to demonstrate the relationship between the regression predictor and the outcome when we had just one predictor, you should know that it's very difficult and sometimes impossible to visually demonstrate a regression with more than one predictor. So we're not going to look at the scatter plot this time. We're not going to go through and draw the line and look at the intercept, just because it's very difficult and sometimes impossible to visually demonstrate that way. So if you're not understanding, well, how does regression explain these relationships? How does regression depict the relationship between a predictor and an outcome? Go back and watch the last lecture video. Go back and watch the prior lecture video for the prior week. However, you should just understand that it functions extremely similar as a regression with one predictor. It's pretty much the underlying math, the underlying equations, and conceptually, it's very similar to regression with one predictor. Beta naught is still the intercept, and beta 1, beta 2, beta 3, all the way to beta infinity, if you had an infinite number of variables, is still the linear relationship between the two variables. It's still the linear relationship between the associated predictor and the outcome. Okay. So if you have any questions about regression with more than one predictor, you should pause the video and email them to me. I'm happy to answer anything. But if you understand it, we're going to go ahead and cover how to do a regression with more than one predictor in Excel. Okay, so we're going to use the data set that should be on the example guide, I believe. If it's not, shoot me an email and I can send you this data set if you want to follow along. So as you can see in this data set, we have job satisfaction, we have conscientiousness, and we have job performance. So we're going to test and see whether job satisfaction and conscientiousness predict job performance when analyzed together. So that would mean, if we're looking at it all in a regression, does job satisfaction predict job performance when controlling for conscientiousness? And does conscientiousness predict job performance when controlling for job satisfaction? So to do this, like we always do, we would first click on data analysis. We would do the same thing we did last lecture. We would click on regression. So just like we did for regression with one predictor, we would just click on regression. And then the same window pops up. So in the same window, we would input the Y range. So this is for our outcome. This is for our outcome range. So we would click on that highlighted button to identify our outcome data. And we would highlight our outcome data. And as you can see on the screen right here, this is very important. We do go ahead and highlight the label. We do go ahead and highlight the label that we want to, of the variable we want to include. So highlight that label, highlight that data for our outcome, which is job performance in this example, and then hit that highlighted button. Next, we want to tell it our predictor data. So we hit that highlighted button that's the input X range button. And then we would highlight our predictor data. We would highlight job satisfaction and conscientiousness. We would highlight both of them. And as you can see, I also highlighted the labels. You certainly need to do this. You certainly need to go ahead and highlight those labels. So once we've highlighted all the predictor data and all the predictor labels, we go ahead and hit that other highlighted button. And then before hitting OK, we make sure we have checked the labels box. So make sure you have the labels box checked. Because we highlighted the labels, we should have the labels box checked. And then we push OK. Okay, so this is our output. This is what our output looks like. Go us. As you can see, the output looks extremely similar to regression with one predictor. Unfortunately, it's interpreted almost the exact same way. So if you did fine with regression with one predictor, which most everyone in the class did, I have no concerns with you, then you should be able to interpret this. So the first thing we want to interpret is the coefficient of our intercept. So the first thing we want to interpret is the intercept, the coefficient for our intercept, which would be our beta naught. So in this example, our beta naught was 1.393. If we rounded, it would be 1.394. So as you can see, our intercept rounded was 1.394. So if the question was, what was our beta naught? We would say 1.394 rounded up. We can also see that our beta 1 is included. So our beta for job satisfaction, which would be beta 1 in this example, was 0.349. And if we rounded up, it would be 0.350. So in this example, we would say that our coefficient for job satisfaction, our beta 1, would be 0.350. And then the last in the coefficient column is conscientiousness. So we would say our beta 2, or our coefficient for conscientiousness, is 0.301. So in this example, it's 0.301. So this was our beta 2. This was our coefficient for conscientiousness, which is 0.301. So from this, we know that the regression equation from this example is y hat equals our intercept, which was 1.39, plus 0.35x1, which was our beta 1. 0.35 was our beta 1, so we plugged that in, plus our beta 2, which is 0.30x2. So overall, our regression equation is y hat equals 1.39 plus 0.35x1 plus 0.30x2. So this is our regression equation we got from our regression results. Next, we would want to report our t-statistics. We would want to at least know where to find them. So our t-statistic for job satisfaction is 2.696. If we round it, it would be 2.697. So our t-statistic for job satisfaction is 2.697. And as you know, that's kind of difficult to interpret. So we would go ahead and look at our p-value for job satisfaction. So this would tell us whether job satisfaction was indeed a significant predictor of our outcome. So we can see our p-value for job satisfaction was 0.012. So it was 0.012. So is job satisfaction a significant predictor of job performance? Hopefully you said yes. Now we know that job satisfaction was a significant predictor of job performance. And we could even say, since we did a regression with multiple predictors, that we now know that job satisfaction was a significant predictor of job performance while controlling for conscientiousness, while controlling for that other variable. So because we had that other variable in there, we could say that job satisfaction predict job performance above and beyond conscientiousness. It was a significant predictor. Okay, so we also want to look at the t-statistic for conscientiousness. And this example was 1.737. As you know, that's difficult to interpret on its own. So let's look at the p-value for conscientiousness, which was 0.094. So the p-value was 0.094. So is this statistically significant? Hopefully you said no. Hopefully you said this was not statistically significant. So now we know that conscientiousness was not a significant predictor of job performance when accounting for job satisfaction. Since we ran it in the regression with job satisfaction, we will know that conscientiousness was not a significant predictor of job performance when accounting for job satisfaction. Okay. And the very last thing we want to look at on this regression result is our r squared. So our r squared was 0.668. If we rounded that up to 2 decimal places, it would be 0.67. And we would therefore know that these two predictors explain 67% of the variance in job performance. So we would know that just job satisfaction and conscientiousness in this example explains 67% of the variance in job performance. So as you can see from all those analyses, from all those results, from everything we just did, regression with multiple predictors is almost identical to regression with just one predictor. If you understood regression with just one predictor, then you should be able to understand regression with multiple predictors, or at least I would hope that you could. So ask yourself if you have any questions at this moment. If you understood all that, good, go ahead and continue with the video. And as always, if not, pause it, shoot me an email, ask me the question, and I'll try to respond as soon as possible. Okay, so now let's talk about making inferences with regression. Now let's talk about making predictions with regression. How do we make predictions with our regression results? So the first question is, what else can our regression equation do? We can use our regression equation, we can use our regression results to predict our outcome given specific values of our predictors. So if we for some reason said, hey, we are interested in a particular set of values for our predictors, we can then try to estimate, given those specific values for our predictors, what would we expect our outcome to be? So if ahead of time we knew that there are certain values of our predictors that are important, we could then get our results and say, well, if those values of our predictors occurred, what would we expect our outcome to be based on those predictors? And we're going to run through an example of doing exactly that. So how do we do this? So first we take our obtained regression equation. First we take the results we got in Excel. If you're doing a different statistical program, it gives you standardized and unstandardized betas. We'd be taking the unstandardized betas. So we'd go ahead and take our obtained regression results. We would take the coefficients as they're called in Excel, and other programs are typically called unstandardized beta coefficients. And we would go ahead and take those and make the formula that you should make. So in the last example, we had our intercept of 1.39. So we would start by our equation being y hat, which is our predicted value, equals 1.39 plus, we would take our beta 1, which was 0.35 in the last example, times x1 plus 0.30, which was our beta 2 in our last example, times x2. So based on our prior regression results, which we had 1.39 for our intercept, 0.35 for beta 1, and 0.30 for beta 2, we would make our regression equation, which would then be y hat equals 1.39 plus 0.35 x1 plus 0.30 x2. Then we would input the predictor values that we're interested in. Then we would plug in for x1 and x2 the values that we're interested in. And if this was a homework assignment, I would directly give you those values. I would say that, hey, your manager is interested in these two values, go ahead and plug them in your regression equation. So in the last example, job satisfaction was the first predictor, conscientiousness was the second predictor. So let's say we're interested in a job satisfaction value of 6 and a conscientiousness value of 3. If that was the case, we would plug those values in for x1 and x2. So then our equation would become y hat equals 1.39. That stays the same. We never multiply the intercept by anything. We never do anything with that intercept. So it would be y hat equals 1.39 plus 0.35 times 6, because we're plugging in 6 for job satisfaction, plus 0.30 times 3, because we're plugging in 3 for conscientiousness. So that would result in our complete equation of y hat equals 1.39 plus 0.35 times 6 plus 0.30 times 3. So that's what our prediction equation becomes. That's what we have to figure out. That's what we have to solve to figure out what our predicted value of our outcome would be given the specified values of our predictors. So moving on from there, we just complete the math. So we would just say 0.35 times 6 is 2.1, 0.3 times 3 is 0.9, and then we will just add everything from there. So if we go 1.39 plus 2.1 plus 0.9, we would get 4.39. So therefore, in this example, we would expect job performance to be 4.39 when job satisfaction is 6 and conscientiousness is 3. And we got that from where we did our regression. We got the coefficients, and then we just plugged in the values we're interested in for x1 and x2. We just got our beta naught, our beta 1, and our beta 2, and then we plugged in those values for x1 and x2, and we solved from there. So therefore, once again, in this example, we would expect job performance to be 4.39 when job satisfaction is 6 and conscientiousness is 3. So you might be asking yourself, well, I don't really like doing things by hand. I find it inconvenient. It's confusing to me. Could this be done in Excel? And the answer is sure. It certainly could be done in Excel. So to do this in Excel, we would just go ahead and run our regression. We would do everything we did before in the earlier part of this lecture in Excel. So if you accidentally closed out of that, or if you did close out of that, go ahead and run that regression again. Go ahead and get those regression results. And the first thing you'd want to do is go ahead and open a second Excel window. Go ahead and open a second Excel window. And you're going to want to copy and paste that highlighted area into your new Excel window. So highlight the 4 cells right there. So start by highlighting the empty cell and the coefficient cell, and then scroll down until you've highlighted the intercept, the 1.39, the job satisfaction, the 0.349, and the conscientiousness and the 0.301. So that would be 8 cells in total you would want to highlight. So the blank cell, the coefficient cell, the intercept cell, the 1.39 cell, the job satisfaction cell, the 0.349 cell, and the conscientiousness cell and the 0.301 cell. So in other words, you're going to want to highlight the labels and the betas. You're going to want to highlight the labels, the beta 1, the beta 2, and the beta 3. So go ahead and copy and paste that into a new Excel window. So open that new window in Excel and copy and paste that. And it should look very similar to this. As you can see, I just copy and pasted the coefficient label. I copy and pasted the other labels, the intercept, the job satisfaction, and the conscientiousness labels. And then I included the numbers. I included the beta naught, which was 1.39, the beta 1 that was 0.349, and the beta 2 that was 0.301. So after you've copy and pasted those 8 cells, the very first thing you're going to want to do is do exactly what I have highlighted right there. Right beside where your beta naught is, right beside where that 1.39 is, go ahead and enter the number 1. And I'll explain why later, but go ahead and enter the number 1 right where you see it on this example. Next, we're going to go ahead and input the specified numbers we're interested in. So as you remember, we were interested in number 6 for job satisfaction. So we would go ahead and enter a number 6 on that job satisfaction row right below that number 1. And as you remember, we were interested in number 3 for conscientiousness. So we would enter the number 3 right below that number 6. So we would have a 1 for the intercept, a 6 for job satisfaction, and 3 for conscientiousness. And then we would want to go ahead and label this column. I like to call it values. So we're going to go ahead and label this column and call it values. So then, now that we have our coefficients, our beta naught, our beta 1, and our beta 2, and we have the values we're interested in this next column, we're going to want to go ahead and multiply those together. So go ahead and multiply the value you're interested in times the associated beta coefficient that it's relevant to. So the very first one would be equals B2, which would be the cell for our beta naught, times C2, which would be the cell for that number 1. And the reason why we're doing that is you don't want to do anything to that intercept. You don't want to change that intercept in any way, shape, or form. So the easiest way to do that is just tell it to multiply it by 1. Because if you multiply anything by 1, it's itself. No matter what, if you multiply it by 1, it stays the same, and we want it to stay the same. So we're telling Excel right now in this new column to take our intercept and multiply it by 1. And to do that, we said equal B2, which is the cell that our intercept is in, times C2, which is the cell number 1 is in. And then we're going to want to do the same thing for the 2 cells below that. We're going to want to tell it to multiply right below what we just did, to multiply our beta 1, which is the B3 cell, times the number we're interested in for job satisfaction, which was 6. So we're going to say equal B3 times C3. And in that one we're saying our beta 1 times the number we're interested in for job satisfaction, which was 6. And then right below that, we're going to want to multiply our beta 2 times the number we're interested in for conscientiousness, which was 3. So we would say equal B4 times C4. So once you do that, you should get the numbers 2.98 and 0.904. So once again, in that row 3 in the job satisfaction row, we're multiplying our beta 1 times the number we're interested in, which was 6. And in the row below that, we're going to take our beta 2 times the number we're interested in for conscientiousness. And then to finish that, we're going to want to go ahead and add the label, which I like to use the label multiplied because it's our numbers multiplied together. And then the very last thing we do is we go ahead and sum up those 3 final values. So we want to go ahead and add those 3 final values together. So I think the easiest way to do that is to type in equal sum. You then open parenthesis, highlight those 3 numbers, and then close parenthesis. So equal sum, open parenthesis, highlight those 3 numbers, close parenthesis. Or if you're following along in this example, you can just retype what I have up there already. So we do equal sum, that will give us the sum. We want to go ahead and label this column. I like to label it sum. And as we can see, this is our final result. This is what our y hat would be. This is our predicted value of the outcome given these specified values. So in this example, given a job satisfaction score of 6, given a conscientiousness score of 3, we would expect our outcome or job performance to have a value of 4.396. So we would have our result be 4.396. And that's all this slide is saying. So as you can see, our final number was 4.396459 to be more exact. And this barely differs from what we did when we calculated it by hand before. When we calculated by hand before, it was just 4.39. And that's just because the values differ due to rounding. Before we didn't multiply the exact values. Now we get a more exact number. So this barely differs from what we did before due to rounding, but technically it is more correct technically. So therefore we can see that we would expect job performance to be 4.396 when job satisfaction is 6 and conscientiousness is 3. And that's how we can do prediction with regression. That's exactly what we're doing here. That we're saying that we're predicting that job satisfaction is 6 and conscientiousness is 3. We're predicting that job performance is 4.396. And you can do this with any application of regression. If we ran a regression of height predicting weight, if we ran a regression of different company characteristics predicting revenue, and we had a result that gave us certain beta coefficients, we can then use that for prediction. We can then plug in numbers and try to estimate, well, given these characteristics of the company, given this someone's height, so on and so on, we can then predict whatever the outcome is, whether it's revenue, whether it's weight, so on and so on. And that's how you make prediction with regression. That's how you make inferences with regression. So that's all for this lecture. It's a little bit shorter than I thought it would be. I'm sure that's because some of y'all might have questions, so please shoot me an email with questions. Usually this lecture takes the entire hour and 15 minutes when I do it in person, because people typically ask me questions during the lecture. So please, if you have any questions, shoot me an email. I'm happy to answer anything, because this ended a lot shorter than I thought it would. So please, I'm sure you still have questions. I'm sure you have something you're confused about. So please shoot me an email and I'm happy to help you out. I'm happy to help you with whatever you need, but you might be good. You might be ready to go. So if that's one of you, if you're the person who's ready to go ahead and look at the guide that's in the comments below and also in the email that I sent to the class, and follow the guide, try your best. And if you have any difficulties, please shoot me an email. If you're confused with it, please send me an email and I'll try my best to help you out. But that's all for this lecture. Thank you for listening, and good luck on the homework.